Hey guys, welcome back. Today we're going to be talking about heat transfer. We've been talking about temperature and energy, and we're kind of building up a case towards something called thermodynamics, which is going to be a couple more lectures away. But we still have a couple more of footstones that we have to put in place before we get to that point. And thermodynamics is really neat because that determines why everything does exactly what it does. Okay, so let's go ahead and start talking about heat transfer. Remember, we're talking about temperature in the last lecture. Now we're going to talk about what happens when heat moves from place to place. And of course, here's an obvious example of heat transfer in this image right here. There's a house on fire. Firefighters actually trying to distribute water to cool down the flames here. And in doing so, that's supposed to help suppress the reaction from happening. So the idea is to be able to slow the heat transfer that is occurring in this chemical reaction. But there's also heat transfer going from the house, which is on fire, into the atmosphere above it. So here we see these plumes rising up. And we're basically transferring heat from the chemical reaction of the house right into the atmosphere. It's heating up the atmosphere. Of course, this is a terrible tragedy, but it demonstrates the physics nicely, where we're trying to cool down or reduce the rate of heat transfer here to be able to suppress the fire and hopefully save a larger part of that structure and hopefully some of the belongings of these residents. This might be difficult considering the fact that it's even burning over here on the side. Anyways, let's continue with our lecture here. So heat transfer and change of phase. Objects in thermal contact at different temperatures tend to reach a common temperature in three different ways. Okay, you can either do it through conduction. Conduction is where heat, in this case, would go up along a wire, or in this case, a hot poker that would be going into a fireplace. So it would be traveling along that through conduction, through the metal. Convection. Convection is where it's moving that hot material through a process of density change, actually rises or moves around away from the heat source, and as a consequence, it moves the energy that it's taking with it. And of course, the third way is radiation. Radiation, there's radiative heat. If somebody was to stand in front of this person, they'd feel no heat, but the moment they got out of the way, the heat would come and warm their hands. So it doesn't mean that it's not convecting around them or whatever, but without that direct radiation, they wouldn't feel the heat nearly as well. Okay, so we're going to be discussing in detail convection and conduction and radiation in this lecture. So the easiest way to think of how heat transfers and how heat moves is to understand conduction first. Conduction is the most obvious way to go about this. So conduction is a transfer of internal energy by electron and molecular collisions within a substance, especially a solid. So in this case, we have when you start to heat things up, you start to vibrate the molecules, and that electron and molecular collisions start to increase, and that increase spreads throughout the population. So what will happen is in this case, this will start to vibrate the molecules quicker, and that will slowly start to cause these to vibrate over time. Good conductors conduct heat quickly. So the word conductor is something that is good at conduction. And substances with loosely held electrons transfer energy quickly to other electrons through the solid. So in this case, silver, copper, and other solid metals. Probably the best of the group is actually gold or silver. But copper is quite good as well as aluminum. Aluminum's not so bad. So here we see a pot, and we can see conduction working here. There's a heat source down here. Of course, this is a thermal image. And we can see that the heat source, which is quite hot, it's red and blue and yellow in this image. It's actually heating the bottom of the pot. Here we see the bottom of the pot is a nice green color, which implies it's pretty hot. And it goes right into the zone of a blue area, and that's actually where the liquid, either the soup or the water is that's boiling in the pot. And it's conducting this stuff right into that fluid. Okay. Notice that the spoon that's sitting inside the pot is relatively cool. So it hasn't quite transferred in yet through conduction. Okay. By contrast, poor conductors are something called insulators. And so insulators are really useful if you don't want the energy to transfer through things. So molecules with tightly held electrons in a substance vibrate in place and transfer energy slowly. These are good insulators. And they're very poor conductors. So really good examples would be glass, like the glass you use in your windows, for example, the glass in the windows behind me. Wool is the reason why we wear wool sweaters, to keep ourselves warm in the wintertime. Wood, paper, Cork. Cork is of course, a kind of wood, and so is in fact paper. Paper is made out of wood. Plastic foam is really a very good one. Plastic foam is used in a lot of coolers, for example, because it's a good insulator. And then, of course, air, it turns out, is also a very good insulator. Thank goodness, because if our daily heat budget from when the sun was radiating us with energy and during the daytime was to radiate back out during the nighttime, we'd freeze to death. Fortunately, air is actually it's a pretty good insulator. It's a poor conductor, so it holds that heat when we're actually going through the shadow of the rotation of the Earth. And we don't freeze to death at night. At least as long as you don't live in the polar regions, you'll be okay. So substances that trap air are also good insulators. We just talked about how air itself is an insulator. So in that case, wool has big open spaces with air. Fur does the same thing, and feathers. And believe it or not, snow is a good insulator. There's a reason why Eskimos are able to live inside of igloos and ice structures for extended periods of time. It's because of the very good insulation that snow presents. It's actually warm inside of these structures while it's cold on the outside. This image down here is kind of cool. This is how the molecular model for a insulator works. You can start moving a spring or a ball on a spring, which these are kind of emulating the molecular interactions. And as long as you're moving it here, these springs actually slow the energy transfer through, so that by the time you get over here, it's actually not as strong. And so this is how insulators typically work. If this was a good conductor, we would see a more rigid, less springy relationship here, and the energy would be transferred very fast. We do kind of need to keep in mind that insulation doesn't prevent the flow of internal energy. What it does is it in fact slows the rate at which the internal energy flows. Just because you insulate something doesn't mean it's not going to get hot or cold. You need to be aware of that. You're still going to be transferring heat. It's just going to be going slow. So an example would be rock wool or fiberglass. Fiberglass is real common. This is actually fiberglass here. Between walls that slow the transfer of internal energy from a warm house to a cool exterior in the winter and the reverse in the summer. All right, so this is pretty common in cool environments, or even in desert environments, because a lot of deserts, even in, say, the American Southwest, say from California to Colorado, it pretty typically will get 105 degrees in the summer and then drop to below freezing at night in the winter. So having these types of insulators is really helpful to keep your energy bills manageable. Okay, so there's another way. This is the second way. It's convection. Convection is the transfer of heat involving only bulk motion of fluids. So this here is actually a thermal convection as it would occur within the Earth. And so the Earth actually has a layer beneath the crust that we live on called the mantle. And that mantle is convecting. And so this is a computer model of what somebody thinks might be happening down in the Earth. And here we can see the hot stuff is rising up like a big plume, like a mushroom cloud, and the cold stuff goes down like a mushroom cloud, almost upside down. So here we see it coming down, that's cold, and here it's coming up, it's hot. So an example of convection would be the shimmer of air above a hot stove or above asphalt on a hot day. Well, I think we've all seen that at some point. That's because the air heats up above the asphalt. It's rising up like a plume, just right here. And visible shimmers in water due to temperature difference. Anybody who's ever been snorkeling will recognize pretty rapidly if there's fresh water that's mixing, and usually the fresh water is really cold, that fresh water mixing with salt water when they're snorkeling will make the water look hazy. And the reason why is because of convection. Mixing that water up is going to be convection. All right. So convection is the reason why warm fluid rises. We remember that air is a fluid, right? Air is a gas, but it's a fluid, just like liquid is also a fluid. The difference between gases and liquids is that air is compressible, whereas the liquid is not. So when warm fluid expands, it becomes less dense and is buoyed upward. Look at this. Here we actually see a fire here. This is unfortunately another tragedy. A bunch of buildings are on fire here. And what has happened is that as they're burning, they've generated lots of smoke. And the smoke is hot, right? That smoke, you'll notice here, is this little area here up above. It's expanded a much larger distance. So what's happening is it's expanding. It's becoming less dense and it's moving up. We've already talked about the principles of that. in previous lectures. It rises until its density equals that of the surrounding fluid. So this could go quite a ways. It could go quite a ways up. So, the example, smoke from a fire rises and blends with the surrounding cool air until you get the exact same density between them. And then it levels off, and it goes off on a nice flat level in the air. Another place that we commonly see it is when we're making, say, steamed vegetables on our countertop. And so here we see somebody here making something and they're playing with the steam. You got to be really careful. We've talked about how dangerous steam could be in the past. Just be aware that this is not the safest thing for this woman to do. But anyway, but you get convection and you can get cooling by expansion, right? So we just kind of hinted at that with the fire, right? The smoke was coming up, and as it expanded, it cooled. That also happens in this case. So an example would be the cloudy region above hot steam issuing from the nozzle of a pressure cooker is cool to the touch. So she can put her hand in this steam. It's cool to the touch because it's expanding. But what do you think is going on? So up here it's expanded, but down here, right where it's coming out, it's under very high pressure and it's not expanded yet. And the consequence of that is to be careful. The part of the nozzle that you can't see is steam, and it's very hot steam. You put your hand on this, and you're going to burn yourself with a burn that it'll take you to the emergency room. So you got to be really careful with that stuff. All right. So a combination of air expansion and mixing with cooler surrounding air is what's going to cool this off from here to there. So the heat transfer is being transferred to the surrounding air around it. Okay, we actually get another kind of little experiment you can do. I just thought I'd say this in passing, is just take your hand and just blow on it with your mouth like a nozzle, and your hand will feel cool when you blow on it. But if you open your mouth up and you breathe on it, it comes out hot. It's basically your body temperature. And the reason why is because there's no air expansion when you have your mouth open. But if you have your mouth closed and it expands out, it cools, and it cools things down. You should play with that. You get the idea of why that would happen. Okay. Another cool attribute of convection is the way that it controls sea breezes and wind currents in general. So we're not going to get into details on wind currents in this class, but just we have some ideas that winds are the result of uneven heating of the air near the ground. And this, of course, occurs worldwide in global air circulation systems. But in general, we should just be aware that it's convection that's driving this. Absorption of sun's energy occurs more readily on different parts of the Earth's surface. So what happens is the sun actually heats the Earth's surface, and the heat is actually generated down here at the surface. It's not the sun heating the atmosphere from the top down, it's from the bottom up. And we'll talk about why that is at the end of the lecture, actually, in a couple of slides when we talk about radiance. But in this case, we can see the water here is about 65 degrees Fahrenheit. Here, the land is about 70 degrees Fahrenheit in the summer, in the daytime. And what's going to happen is this is going to be warmer. It's going to cause the air to rise. It's going to convect up. And this other material down here is cooler, and so it's going to be drawing down on top of it and creating a convection current. Okay. At nighttime, the exact opposite happens. Usually, the water temperature doesn't change that much. The water temperature is usually pretty uniform day and night. So at nighttime, it might drop a degree, if that, but the land will actually drop considerably because it has different thermal properties. And so what will happen is the sea breeze will reverse the other direction. If you ever live next to the coast or you ever get a chance to experience this day and night, you should go and see that, run that experiment and see if in fact this is happening where you live. All right. Oh, so we're actually to it quicker than I thought. Radiation. All right. Radiation is a really interesting phenomenon, and it's a very debatable phenomenon, at least up until about the last 100 years or so ago. Before then, a lot of people had some debates as to whether or not it could happen the way that they thought. Okay. Let's talk about what radiation is. So radiation is simply the transfer of energy from, in the case of the Earth, the sun through empty space. So that's where we get all of our radiative energy from, is usually the sun. We get a little bit from the stars, a little bit reflecting off the moon or whatever, but overwhelmingly the sun is in control. Okay? So radiant energy is transferred energy. It radiates out. It exists as electromagnetic waves. We haven't talked about electromagnetic waves that much yet, but we're going to be doing units on it very soon. Really neat stuff coming up ahead of us, so you want to make sure that you're ready for it. Electromagnetic waves ranging from long, say radio waves, to short wavelengths, which are X-rays. So down here we'd see our X-rays here. Actually, they go up into something called gamma radiation, which is in interstellar space right here. And then, of course, radio waves are way over here. And the visible region ranges from long waves, which are red. So here's the red. Notice that this is a longer wavelength here, to short waves, which are violet. And these are shorter over here. This is what we call the visible spectrum. And the visible spectrum is what we, as human beings, are able to see, because that's the maximum radiation exposure from our sun. Our sun emits almost all of its energy in this zone. It also shoots out X-rays and gamma rays and microwaves and radio waves and all these other things too. But most of the energy is available to us as visible light. Okay. So here's a few more things about wavelength of radiation. Basically, it's related to the frequency of the vibration. So here we see a girl moving a rope up and down, just shifting it up and down. And if she does it rapidly, in other words, she does it with a high frequency, it takes on this shape down here. And in doing so, notice that the wavelengths, which is the distance from, say, the top of this wave to the top of that wave, shortens up. So now it's only from here to here. So increase in frequency reduces the wavelength. And that's something that we should be aware of, is we could just simply transfer different kinds of radiation. Let's go back to that other image. Say red into green simply by changing the wavelength, right? It's not necessarily an energy difference. It's just simply a wavelength difference. Okay. High frequency vibrations produce short wavelength waves. We should be careful of how much radiative energy comes to us. Here's a image that kind of demonstrates that if you get exposed at too high of a radiation point, you wind up turning into a sunburned human being. So you got to be careful about the amount of radiation you absorb. So the emission of radiant energy is kind of a neat thing, because it turns out the sun is not the only thing that radiates energy. It turns out all things do. Every single object, not just the sun. So every object above absolute zero radiates. Remember what absolute zero was? It means no vibration. That's the coldest that you can possibly get. You get at 1 degree Kelvin. I shouldn't say 1 degree Kelvin. If you get at 1 Kelvin, you're radiating energy. You're creating radiant energy. So from the sun's surface comes light, called electromagnetic radiation or solar radiation. From the Earth's surface comes terrestrial radiation in the form of infrared waves below our threshold of sight. So we can't actually see infrared. It's not something we can see. Let's go back to that image. So infrared is down here. This is our visible spectrum. It's this little zone right here. But infrared, which is right over here, is what the light is reflected off the Earth as. Okay? And that infrared light we feel as heat. We feel it as warmth. So let's keep talking about this emission of radiant energy. So the frequency of radiation is proportional to the absolute temperature of the source. So if we know the absolute temperature, and our absolute temperature is always measured in Kelvin, it's going to radiate some type of energy. We just described that. But what is that going to look like? Well, it turns out that if you are able to get it at a certain temperature, it's going to produce these frequencies of color, right? And so, for example, this one is at 3,200 degrees Kelvin. This is 2,400 degrees Kelvin. This is at 1,600 degrees Kelvin. Here's the frequency. You have a red, green, and a blue. And this is the visible light spectrum. So we could see this. And that explains why when we heat up steel or we heat up copper or anything like that, it heats up and it glows, right? In this case, this is a white metal, and this implies that it's at about 1,500 degrees Celsius. It's really, really hot, white light. So the range actually matters. Temperature above 500 degrees is red. Above 600, it goes to yellow. And then above 15, it goes to white. And so this is considered white radiation. And you'll notice that the person that's working this is wearing a special suit. He's not worried about the splatter of the iron that he's pouring, even though it's probably very dangerous. The main thing is that he's being directly irradiated by the light coming off of this operation, and he can get burned very severely from it. So in the same way that objects radiate at a certain wavelength, and eventually can, if they get hot enough, emit visible light. Objects also absorb radiant energy as well. And it occurs along with emission of radiant energy. It's usually a compare and contrast. You'll get a certain amount coming in and a certain amount going out. And there's a balance that's going to occur. So what are the effects? So the effects of the surface of material on radiant energy, any material that absorbs more than it emits is a net absorber. So if you have something that is constantly taking in energy but only emitting out so much, it absorbs that energy, which means it's building up that energy. It's getting hotter. Any material that emits more than it absorbs is a net emitter. Those things happen. A net absorption or emission is net absorption or emission is relative to temperature of surroundings. So you always got to compare it to the surroundings, right? If it's something that's going to absorb above a certain temperature, but reflect it below a certain temperature, that's going to be something you got to keep in mind. So it's object specific. Good absorbers are by definition also good emitters. And poor absorbers are poor emitters, right? Because it goes hand in hand. So for example, a radio dish antenna that is a good emitter is also a good receiver. And by design, a poor transmitter is a poor absorber, right? So you just kind of got to balance that in your mind a little bit. Something that's able to receive or something that's able to absorb a lot of energy is also going to be a good emitter of energy, okay? So let's look at reflection of radiant energy, right? So we talked about how things can get absorbed or pulled into matter and actually affect its temperature. What if it reflects off? Well, first off, reflection is opposite to absorption of radiant energy, right? So any surface that reflects very little or no radiant energy looks dark. You can't see it. Look at this. Here we see a nice sunset coming down. Notice that we see a good reflection off the lake, but here we don't see anything being reflected at us. This is the land surface over here, and it looks dark. Another example would be eye pupils. That's the center of your eyes. Open ends of pipe in a stack. Because there's no light coming through, you can't see it. Open doorways or windows of distant houses in the daytime, and so on and so forth. We've all kind of experienced this at different times. So this is the origin of dark objects, largely, especially if they're being irradiated by light. There's just nothing being reflected to our eye in here. It's all being reflected somewhere else, so we can't even see it. And if it's being reflected at all, it can actually be completely absorbed. And of course, radiation is not consistent on Earth year-round. This is what gives rise to our seasons. The reason why, of course, the Earth is tilted. But let's look at this here. So here we can see the month. So this is August, September, October, November, December. We're in winter. The blue areas of low radiation, and we're heading into summer. Look, June, July, look at the radiation. August, now all of a sudden we're in October, November. You can see that moving back up and down. Look at this belt right here. It's going to move up and down year-round. So this is kind of up in the upper hemisphere now, and now it's moving back down into the lower hemisphere. Back and forth it goes. Okay. This change is the reason why we find that we get in the northern hemisphere, we get winter is what is happening here, and summer down in the southern hemisphere. They're at opposite responses, and that's because the radiation is not equal across the Earth at all times. And of course, you can't really talk about radiation without talking about solar power. All right, so here we see a huge power plant. These are a bunch of solar power panels that are out in the Mojave Desert of Southern California. And basically, more energy from the sun hits Earth in 1 hour than all of the energy consumed by humans in an entire year. All right, and that's according to Nathan Lewis at Caltech. That's a lot of energy that's hitting the Earth. Of course, we only have solar panels that we can cover so much of the Earth with. But 1 hour of energy hitting the Earth is a lot of energy. Okay, So here we can see these power plant, or this power plant is just sitting there generating electricity like crazy, so long as it has sun, right? If there was a cloud cover, we'd have problems. All right, so let's finish up. And of course, you can't really get this far without having to bring up our friend Sir Isaac Newton again. It won't be the last time we bring him up, but here he is. Sir Isaac Newton not only did forces and gravity, he also looked at temperatures and optics and things like this as well. And he made some pretty astute observations. Notice that the approximate proportion to the temperature difference, or delta T, between the object and its surroundings was very important in looking at how things cooled off. So it turned out that the rate of cooling was proportional to the change in temperature. So if you're taking something that is really, really hot, say a boiling pot of water, and you want to bring it down to room temperature, the rate at which that happens is proportional to the change in temperature. So for example, let's give some examples. It's really kind of the easiest way, and I've got some written out here. A hot apple pie cools more each minute in a freezer than if left on the kitchen table. That's because you're going to have a higher rate of cooling because the change in temperature is greater. If this is greater, this is greater. And if this is greater, then this is greater. That's how that works. A warmer house leaks more internal energy to the outside than a house that is less warm, right? Because the change in temperature is smaller. Therefore, the rate of cooling is going to be smaller. You're going to not lose as much. It applies to rates of warming, right? If it goes the opposite, if it applies to rates of cooling, it's going to apply to rates of warming as well. It's just in the opposite direction. So object cooler than its surroundings warms up at a rate proportional to delta T, or the change in temperature. So example, frozen food will warm faster in a warm room than in a cold room. That's so intuitive. We're so used to it. But the fact that Sir Isaac Newton was actually able to put kind of a theory to it, he actually put more than just what we have here, that the rate of cooling is proportional to the change in temperature. He had a lot more to say about it than that. But nonetheless, the law holds. And anyways, with that said, we've kind of covered how things move. Remember, we've got conduction, convection, and radiance. And then don't forget Newton's law of cooling that talks about the rates. So it's a kind of a short little lecture, but it goes well with what you're doing in the homework. If you have any questions or you're confused about any of this, as always, meet me on the message boards or send me an email. Until next time, bye.